Okay, so talking about local polynomial regression, and this is a type of non-parametric regression. And I think that whether or not you use it, you probably will at some point. You know, if you take a job somewhere and you're an analyst, I think there's a good chance that you'll use it. Maybe a lot of you already have. So local polynomial regression, or sometimes you see the name. Let's see, Lois, or even Lois. You see that? So this stands for local estimation uh, uh, with scatter plot smoothing. Kind of a weird name. But I think a better name for it is local polynomial regression. And it's a very flexible type of non-parametric regression where you don't have to make any assumptions. Like we talked about spline modeling, where we can get a flexible spline model, but you have to figure out where the knots are going to go and how many knots you're going to put in there. Obviously, there are some techniques that can help you pick the number of knots and where to place them and stuff like that. You don't have to do it manually, but still there's that issue of how to select those. With local polynomial regression, you don't have that hurdle of figuring out the knots and where they go and stuff like that. So it's has an advantage because of that. Its disadvantage is mainly that it's very computationally intensive. Okay, so you think of doing like a mixed model fit, or it could even just be a general linear model, just a regression model that you're fitting. You think of doing that, right? You actually have to repeat that. If you have a bunch of time points, if you have 200 time points, you do that across all your time points. So you're actually, fitting a model that sometimes, it takes a little bit to do that. Then think about repeating that, maybe a couple hundred times. So if you have a big data set, this could be very intensive computationally. But the way things are now, I mean, we have computers now that are pretty fast. So for most data sets, as long as they're not too big, it's still not that big of a deal. But you do have to decide the amount of smoothing that you're going to do. Okay, so let me pull up a data set that we're already familiar with. This is, if you remember, the San Luis Valley data set, and I think I put this supplement on Canvas. If I haven't, I will. But this is like when we were trying to figure out trends over time in hospital counts, and then we were trying to relate that to air pollution, PM10, and we were adjusting for average time trends. And so our initial step was, how do we estimate that function? But before we actually get the splines and figure out, that, we just want some sense of the pattern of the data without any parametric constraints. So if you do proc Lois, and you can do a similar thing in R, here are the hospital counts, and then you can see a gray line. This graph is obviously not real easy to see, but you can see the hospital counts, and then you can see a gray line. This is the Lois curve, and I use a smoothing parameter value of 0.15, so that goes from 0 to 1. And there's actually like AIC type statistics that you can use to figure out the best smoothing value, but sometimes, I mean, just looking at it will give you something pretty intuitive. So I repeated this because that was kind of hard to see, the gray function. I repeated it, and this is the trend we saw in the average hospital counts over time. And so we get a kind of a fit that we can better understand the, did you hear what I did? I actually put my name in that by mistake, but so you can actually get the average counts over time and see what's going on. And we get these peaks that happen every year or every 2 years. And we've talked about, the reason for that. It's typically like flu or some type of yearly issue that's going on that gives the peaks. And then you have in the middle, you have a dip. So this is a pretty flexible way of getting a mean function. And you can think of it as averaging data around a certain localized point. So let's say July 2015, you want to get the best idea of what the mean count is at that time. And so if you just take the average of the points around it, right, that would give you one way of estimating it. And then if you use a moving average, you're going to get some sort of feature like this, that kind of gives us an idea of the mean process. So that in its simplest form would be a simple type of Loess regression. But it's a little more complicated than that. It's a little bit more than just averaging points around a focal point that you're looking at. So we'll talk about those methods, but I just wanted to show you that, sometimes we do Loess regression as an initial analytic method to understand a mean process that's not constrained at all parametrically. And then from there, you can decide, should I use, spline modeling? Is maybe polynomial modeling actually going to work for the data? If I get the right order polynomial. So, it's a good initial tool, I think, to look at the data. And so we've seen that. So today we get more into the methods about how it works, and we actually see how we can use it in conjunction with linear mixed models to estimate a mean function and then to estimate subject functions that veer from it. So one of the differences that we're going to see today with these methods is that we're estimating a smooth function that's not constrained to, follow some specific parametric model. So some points there, which I've kind of covered. So I think the first thing that I'm doing here is I'm just talking about the different types of non-parametric regression techniques that we have in our toolbox, and generalized additive models, which I don't get into too much, but that was actually in that other supplement as well. That's a method that allows you to add a mixture of parametric and non-parametric terms to the model. And there's a proc GAM in SAS, and I'm sure there's also something similar in R that you can use. So GAM, generalized additive models, that's semi-parametric. You can kind of do a mixture of both parametric and non-parametric. The spline modeling is also something that you can use kind of more in a non-parametric direction if you put enough terms in there. Or you could consider it really as a parametric technique. But the Loess regression is really truly I would consider a true non-parametric regression technique. So what you do in Loess regression is you consider one X point in your data, and you're going to perform a local regression at that point. And so the way you do that is you're considering whatever X is usually time, but it doesn't have to be. So the data is centered about that time x naught, okay? And you're gonna do a weighted regression where you're gonna weight the points that are higher, that are closer to x naught, and then downweight the points that are further away, right? Because you want the points that are close to x naught to have the most contribution to the estimate. So you can think of doing a local regression, and again, in the simplest form, it would just be taking an average of points, but weighting the ones that are closer. So you fit a model, and that's going to actually just produce 1 point. It's going to be an estimate of the average y that's meaningful to that 1 point. Okay, and then you repeat this process over multiple x points. Okay, so again, it's a pretty computationally intensive process. And we're going to see, though, that you don't necessarily just need to average points. We're going to actually do a linear regression or quadratic regression about that point, but still just take the intercept value that's centered about this point, x naught. So how do you weight the points? You know, you want to give higher weight to the points that are closer to x naught. One simple way would be to use like a standard normal kernel, because we know the standard normal has, you know, the highest weight in the middle, and then it tails off as you get further away on either side, and it's symmetric, right? So that would be one possible weighting function that we could use. And the amount of smoothing that you do is going to be controlled by h, which is called the bandwidth. The higher the value, the more smoothing that's going to occur. And the lower the value, the more that the estimate's going to follow the data, right? So in statistics, what we want to do is we want to find an average trend that is not too smooth, because if it's too smooth, then, you know, you just have basically a flat line, right? And if it's not smooth enough, then you're following trends that may just be arbitrary. They may just be error, right? So you have to find, like a lot of things, you have to find a happy medium where you're describing the data, but not over describing it. Okay, so that's one of the goals, is to figure out what that bandwidth value should be. Okay, so that's one approach. Another approach you could do is just to say, let's take a certain number of points within that focal point and just average them. So that you'd be applying like a uniform kernel, and you'd say, well, I know I'm not going to, if it's too far away, I'm not going to use it at all. But as long as it's within a certain range, I'm going to use it and just use an average. So that'd be like using the uniform kernel. So you can actually do a hybrid of those two. You can do something that weights points higher if they're closer to the focal point. But then also say, well, I'm not going to consider points that are too far away. So that would be using something like this. Now the tricube function, that's a lot like the standard normal. It kind of has appearance where you have kind of a mound shape that has a peak in the middle, and then it kind of tails off. But it's just a little simpler function, but it kind of looks similar to the standard normal kernel. So again, there are specific you know, optimal values that you can get through like AIC type statistics or cross-validation statistics that will tell you this is the optimal bandwidth. So those are things that you can use. But it's funny because I've actually found that, you know, when I look at those and I look at the, you know, the smoothness of the function, to me, sometimes it doesn't seem as intuitive as something that I would just use by sight. So, you know, you know, statistics I think, again, you have to kind of have these things available and realize that we have these, goodness of fit statistics that we can use, but you can also look at things and make sure they make sense visually. So I wouldn't get too caught up in just saying, okay, here's a method, let's use it, and not even think about what's happening. So what we do when we do our local regression, usually you're going to add a first order term in there. So if you do a first order, it's called local linear regression. And if you do a second order, it's local quadratic regression, rather than just averaging the points around it. And so why do we need to do that? Why do we need to add a linear term there if we're only going to take the centered intercept out of there? The main reason, as I've stated here, is that it reduces bias in the estimated function. And that's especially true on the endpoints. We can talk about that more later, but it specifically allows you to use a larger bandwidth, producing a smoother function without inducing as much bias as you would have for lower order polynomials. Okay, so I'll give you an example here in a second about how this works. And this data set is a pretty old data set. Fox is a guy who wrote several textbooks on nonparametric regression and local regression in particular. And so this data set is sort of a popular one, but it's an older data set. This is occupational prestige data. So we're looking at salaries for people in Canada in 1971. So that's, almost 50 years now. And so when you look at the values, my first thought was, 8,000, we're going to see values between like 0 and 25,000. I'm thinking, is that monthly salary? It was actually a yearly salary in Canada. So you can kind of see the amount of inflation that's occurred over the last 50 years. So 8,000 was sort of in the middle. That's around the average. And there's some measure of prestige that they have, like what people think of this occupation. Is it a prestigious occupation or not? So there's some survey that was given where they collected that information. Okay, so in the graph, there's 4 panels, and this just talks about each plot. So I'm going to show you the plots. So this is the data in panel A. That's just a scatter plot of the level of prestige that people thought of this occupation, and then the actual average yearly salary for that. And so you can see the pattern. It's not too crazy. It's not like the San Luis Valley that, he had a lot of humps going through and a lot of time points. So a little simpler, but still it's not exactly clear just from looking at it if there was a parametric function, what you'd fit to it. So we're going to use the local polynomial regression, and we're going to consider, in the first case, this 8,403, and that's our local point for this one regression that we're going to do. And so if we use a tricube function, which has the shape that's shown in panel B, so you can see the higher weight's going to be given to points closer to that point 8,403. And we're also going to only use the points that are within this window, which is roughly half of the points. Okay, so we do one regression, and it's a linear regression. We can see what's going to happen. You get this estimate, and we center the intercept about that focal point. So the intercept value is going to be that black dot. we do this one regression to get that 1 point. That's it. And so what you do is you repeat this process across different incomes, and you get this function in panel D. Okay. So again, one of the points I'm making is that, you know, if you just average the points here, you might get something close to that, but we actually do a linear regression, and then we have a centered intercept, and we get the value, you know, again, because of the point that I brought up before about reducing bias and so forth. And you can think about, especially at the endpoints, this is going to be important because let me do another one over here. If we had, let's say we have points coming up like this. Okay, maybe in the middle here, if you're just going to average the points, you'd be okay, right? But what's going to happen if we do a local regression right here? You only have points on one side, right? So you can really see some of the problems you get if you just take an average of the points around it. You're going to get something that kind of tails off this way, right? And goes a little bit low. Whereas you really want the function to keep going this way. And by doing by adding the linear term, that'll help you, right? To maintain the pattern of the data. So you can really see the issue, especially when you look at the endpoints, but it's going to be true in general as well. Any questions up to this point? Okay, we'll keep going. So in that last figure, what we did to exclude data points, you know, so what did we decide to exclude data points here? We only used about 50%, it was actually 49% of the data. And as you move, you're only using a window of a certain percentage of data, right? So that's what we call the span. So that'll act like the smoothing parameter when you join that with the tri-cube function, and then how much data you're going to use around it. Okay. So the question is, how do we take this concept and how do we add the longitudinal component where we have repeated measures on subjects? We can actually use the same principle, right? Where we have a local regression and we get some estimate, and we can generalize this by considering subjects as random effects, right? So if we add subjects and we add a random intercept and a random slope for time, you can actually get two things. You can get an estimate of the mean process at a given point, and you can estimate subject deviations. So if you can do that at one focal point and you repeat that process, you're going to end up with two different functions, two different types of functions, I should say. A mean function across all subjects, and then subject-specific functions across time. Okay, so it's a pretty straightforward extension, I think, to go to longitudinal data where you have repeated measures on subjects over time. So as I'm bringing up, you know, those functions that I just mentioned, it kind of requires us to define a new model in this situation. And so we have these functions. We have our overall mean. Okay, so that could be like with the last example I talked about, that's the the level of prestige for that data. I'm going to show you another example where we're looking at FEV1 lung function measure over time for subjects. So whatever outcome you're interested in, we still have Y as the outcome, but now it's a smooth function. Instead of one value, you have a smooth function over time or whatever predictor of interest that you have. And so to make that, what I'm going to use in notation is I use Y and then subscript I for subject I. And this eta sub t, this is going to be the population mean, smooth function. And then we have an error function. So that's if you just have, you know, an overall mean that you're estimating, a mean process. If you have subjects that you want to estimate in their process, then here we still have our population mean, and then we have our subject deviation, and then we have our error. Okay, so it's very similar to what we talked about before, but now just think of, instead of individual values, you actually have a smooth function, okay, for your outcome, for your population mean, for your subject deviations, and for your error. So to actually get the subject specific functions, you would add the population mean plus nu of t. Okay, but it's analogous to our linear mixed model. It's just now that we have smooth functions. So, like I mentioned, we're going to use the same idea. We're going to use linear mixed models to do this, and we're going to do local polynomial regression, where we're going to add a random intercept and a random slope for time. But it's the same principle. You do a local regression, and then you repeat that process over your time points to get your smooth function. So this is going to work well if you're going to, if you have growth data that you're not certain, again, if you're not really certain about the specific function that you should use, if you don't have an idea about the parametric function, and maybe it's an initial step in an analysis, maybe eventually you'll find the parametric function that might work. But right now you want to do an analysis that's not constrained. You just want to look at the data, get a sense of what's happening with the data without making any assumptions about the model. So there's pros and cons to this regression. The pro is it's very flexible. You're not constrained. The downside is you don't have a nice summary in terms of beta coefficients to describe that function. And so what you end up with, the thing that you use to describe what you have is usually a graph. Okay, you can also make a table and put your time points and then put your estimate. But the thing that's most digestible, I think, is typically a graph that shows, the original data and then what the estimated means are, those continuous functions over time. The graph is usually the most easy thing to digest with this. As far as, picking the best levels of smoothness, we typically use cross-validation statistics to do that. And there's pros and cons to this. One of the things that it requires even more fitting to do this. And so I had a student, Ed Hess, I don't know if anybody of you know him, but he works at I think he still works at the VA. and he was a student in one of the first classes I taught. But I worked with him on his master's, and he used the data that we're going to see in a second. And he used these statistics. So you actually have two separate levels of smoothness. One for the population mean function and one for the specific subject-specific functions. But you essentially use cross-validation statistics to do this. And so not only are you fitting all of the time points that you have, or whatever number of time points you feel you can get to describe that function, you have to do even more to figure out the optimal level of smoothness for these functions using cross-validation. So I'm going to jump to the application. So we're looking at FEV1. So it's a lung function measure over time. And it's the same data that I've introduced before. The students that go to a school here at National Jewish, they were monitored over time. And the main point of the study, again, is seeing how their health related to daily pollution. That was like the main goal of the study. But this analysis, we're just trying to understand lung function and how it changes over time. And we want to get an idea about the overall average for these kids, but also are there certain patterns that that kids exhibit, especially as you go from one season to another, and maybe there's more allergens in the air, and certain kids may respond more to those, and so you might expect that their FEV1 will go down if they're being challenged more with the type of allergies that they have. So we just wanted to understand the kids and their FEV1 over time, and then also the overall average. So we took one school year, and we figured out, with the cross-validation, the optimal level of smoothness that we wanted to use for the overall average, and then also for the subject-specific functions. And so there's graphs coming up here I'm going to show you. So here's the data, and I only have two subjects here because there's a lot of data, and this is more to demonstrate the difference between the population mean and the subject-specific functions. So the solid line is the average, and what did we call that? Was that eta? So this is eta sub t. That's this function here. That's the overall average. So that's average FEV1. FEV1 is measured in liters, right? And the higher the number, the stronger the lung is. But it's also dependent on age, because especially the kids at this age, they're growing. And so you'd expect, over time that average is actually going to increase. And you see that even over, a period of a couple hundred days, you can see a slight increase in that function. Now, in your modeling, a lot of times what we do is we would put in age as a covariate along with other factors like height and gender, race, things like that. But here we're just measuring raw FEV1, and so we would expect a slight increase, as the kids are growing, even within a couple hundred days. There's a lot of growth occurring for these kids. It's like my son, who he puts on his pants, and I can tell how much he's grown by looking at how short his pants are right now. He's a sophomore in high school, and he's really gone through his growth spurt right now. So what I did, I also put in two subjects. So the filled in circles are one subject, and the open circles are another subject. And I put in there subject specific line. So this would be the overall average plus nu sub t for that one subject. For now, I'm just going to call that subject 1. But these are estimated, right? And then this is another one. This would be the overall average for another subject. So this piece, the nu, that's the deviation. It's going to start messing with me again. This piece here, all right. Two can play this game. This is very unbelievably stubborn today. Okay, the 10th time's a charm with that. So there's our estimated mean function for that second subject. And so you can see that, one subject, well, this is quite interesting because you can see this one subject who's above the mean is pretty consistent, right? And over time, what do you notice about their data relative to this subject?
The spread is really small.
Yeah, so this one subject, they're very consistent. The spread is very small. This subject has much more variability. Okay, so that's pretty striking, to be honest. This is quite striking, that how much higher the variability day to day the FEV1 values are for this one subject. And another thing you notice is that this one subject, they pretty much follow that mean trend, right? Because there's a slight increase for that subject, whereas this one is moving around more and actually goes down here. Maybe I think this is in the spring, and maybe they're being affected by allergies more. So this allows us to see individual subjects, what's happening to them, and we can target them. We can go in and say, look, we notice that you have these patterns. We want to try to possibly monitor subjects like that are struggling more during certain seasons, and maybe even try to figure out how can we help this one kid, who seems to be having more trouble during this time relative to other subjects. Okay, so the question is, when we fit this model, what does it look like in SAS or R? You can do it in either one pretty easily. So we mentioned
Quick question, Matt.
Yeah, question?
Yeah, so would it make sense to fit the same fit the same low S with the same smoothing parameter for subjects that are
it's funny that you mentioned that, because I was just thinking the same thing to myself, that we use the same smoothness, right? But that question, that I thought about that as I was walking through this myself, is should we use a different smoothing parameter for different subjects? Obviously, that you have to draw the line somewhere, right? That maybe you want to group subjects into the low variability versus the high variability groups. I think it would be pretty tough to try to get one parameter and use that for one subject and then change it for the next and then change it for the next. That would be pretty intensive, but this graph, I think, does suggest that maybe you can at least pool subjects into low and high variability types and maybe use different levels of smoothness. But the thing is, with that one subject with high variability, if let's say you use a higher value of smoothness, Well, just think about what you might be doing for that subject, right? If you increase the level of smoothness, then you may get something like this, right? That's going to follow the points around more. You have to be careful, right? In doing that, there's a balance. Again, there's a balance you need to consider of what is the right level. You don't want to start chasing trends that aren't meaningful, right? So, but that's a good point. You know, you maybe consider a few groups of subjects, and you don't necessarily need to use the same smoothing parameter for all subjects. So we've talked about these trends for individual subjects. Here's the code that you can use if you're just focused on one time point, and you know, we can use proc mixed and SAS. We can use be tough. We'd have to use the LME function here because I've added a random term and a repeated, right? And so you'd have to use the LME function in the NLME package, which you know, sometimes I get results that make sense and sometimes not. You could maybe consider in R, you could consider the LMER function if you were to remove the repeated statement and just have the random statement. And maybe that would be sufficient for the repeated measures, although I think this the good thing about this is it allows us to get subject specific estimates. And then we're also handling any leftover serial correlation in the data. Okay, so what we do is we create, in our data step here, I'm just looking at time point 30. Okay, so if you look at the graph, that's early in the data, so that's about right here. And I'm doing one local regression about that point. And so I'm centering delta. This is our x minus x naught. I call it delta. And I'm using this bandwidth here. And I create the weights using I'm using a standard normal. So I'm not using that tri-cube function. I'm going back to a standard normal to create the weights. So the points that are closer to our focal point are going to have higher weight, and as you move away from that, they're going to have lower weight. But I'm not restricting the data to only include a certain amount. I'm just using the weight function to have either higher weight or smaller weight as you get closer or further away from the focal point. And so in proc mixed, all we have to do is add this weight statement that's gonna allow the weighting. And I have delta, that's this thing here, x minus x naught. Automatically, there's going to be an intercept in there, right? We know that when we do proc GL and proc mix, those things. And I think R is the same, right? Automatically you have an intercept value. Then we have a random intercept, and then the linear term for time, which is, you know, delta. So I fit that model, and then I just pick off the fitted intercepts for the overall mean function. And then for the subject specific deviation. So here's the mixed output that you get, and here's the intercept value using the centered data. And so this is going to be our estimate of eta at time 30. And then if you say solution in the random statement, you're going to get, you know, the subject specific deviations. And so that deviation for that one subject is going to be our estimate for nu at that same time point. So we have 1.596 as the overall average. And then that one subject's going to be 0.13 units below the mean function at that time point. Okay. So let me just run back to this. So at time 30, actually, I'll use an X. This was the 1.5963, was it? And then this distance was the negative 0.13. So that's focusing on that one time point, right? That should, sorry, being perfectionist here. So we're focused on that one time point as we go up. So the negative 0.13, that's the deviation. So if you add those two together, then you get your that estimate at that time point right there. So how do you combine those? You have a population average estimate, and then you have random deviation. How do we combine those? We haven't talked about this yet. If you have both fixed effects and random effects that you want to add together, you can do that in the estimate statement by including this bar. So everything to the left of the bar is going to be fixed effects estimates, and everything to the right is going to be random effect estimates. So these are the fixed effects. In this case, it's just the intercept, right? And then everything to the right of this bar, these are going to be the random effects estimates. So you can actually, through the estimate statement, you can incorporate random effects into that by including the bar. One of the painful things though, and I've tried to find a solution to this, but to identify which subject that we want, we need to list out, we need to have a place for every subject in our data set and then indicate which subject that we want the estimate for. And I've tried to figure out can't we compact this code? And I haven't really found a way to do that. So we identify that one subject that we want, and we're going to take that intercept deviation for that subject and add it to the population average. And so this is a combination of the 1 point, just below 1.6, and then this should be on one line, the negative 0.13. So that's the 1.5963 minus 0.1324, and we get that 1.46 for that one subject at that one time point. Then you repeat this process over the time points that you have to get those smooth functions. In our case, we had a couple hundred days, so we did it for each day. And we obtained the population mean, and then for every subject, we have a function over time that's flexible that we can understand what's happening to their health during this study period. So this is just talking about the computational intensity that it requires. it's usually not too bad. I think what I found was it became difficult when we started doing the cross-validation statistics. It's not impossible, but you know, this data set is not that big really. But doing the regular lowest regression was not that intensive, but in order to get the, you know, optimal smoothing values, you know, using cross-validation, that was the thing that was a little more intensive. And then Ed Hess did his master's regarding this data that we saw. Any questions?
Did you say the intercept that we estimate from that model with the window of data needs to be centered?
Yes.
How do you do the centering in the code there?
The way you do that is by, you do it by centering X. So by using, we add delta, right? Instead of just time, which would be the 1 through, you know, 199, whatever variable we use for that, it would be day actually, I think. So if we had put in day here, then our intercept would have been in front. But the fact that we're using a centered time variable, that's automatically going to make the intercept be right at that point, that focal point. So that's how you do it. You by including that delta time instead of the regular time variable.
Cool,
Yeah,
thanks.
question. Yeah, good. What else? Does anybody have data that where you have like a trend over time? You might have a lot of time points, but where this might be a method you'd apply, either this or the spline modeling. Does anybody want to mention the data that they're working with?
I'm looking at data from NBA games, like every single game of like 8 seasons. So it's just like a ton of repeated measures. Maybe I should try this.
Yeah, I guess the question is, yeah. So if you're looking at games, there's 82 games, right, per season. And if you're so yeah, you might have a lot of time points. I guess the question is, you know, how do you join the years together? Because there's that gap in between the seasons. So you have to think about how to do that in a meaningful way. There'll be a lower gap this year, right? They finished the finals like a month or two ago, and I think they're planning on starting the season again in December for the NBA. So yeah, so I guess that's the question for your data is how do you join those years together and you know, in a meaningful way? Do you leave that gap in there, or do you just kind of end the, you know, one season and go right into the next one, or so forth? So I have to think about that. Anybody else have like data with a lot of time points?
Not for my project, but for one of my work projects, I have 8 years of births, and it's a counting of like preterm births each month, and so it adds up pretty fast.
How many time points are there total? You said 8 years. Is it?
Yeah, 8 times 12, whatever that is.
Okay. Yeah, you know, so I would encourage you guys, like, you know, the lowest, like whether you need to include, account for longitudinal data or repeated measures, that's maybe a secondary issue, but you can always use, the proc LOES, or I think there's a LOES function in R as well, just to get an understanding of the trends in the data, and if you do have repeated measures on subjects, you can still just use the simpler form just to get an understanding of that mean function over time, the population mean function. And that's typically what this stuff is used for, is like as an initial step. In some cases, it might actually be the final product as well. But a lot of times we use it just to get an initial understanding of the trend in the data. I'm going to run back actually to the first example. And with the prestige data. And look at this trend in D. Does that suggest to you any parametric function? And I'll tell you this. I don't think the quadratic is going to work. There is one major change point, right? Or point of inflection, or whatever you want to call it. I guess it's not really a point of inflection. It's a curve, right? But there's one point where that seems to be occurring at. There's a couple functions I can think of, but what do you think about modeling if we were to try to find a parametric function for that in D?
Maybe a gamma?
Gamma. I hadn't thought about that. What makes you say that, gamma?
Looks like a gamma to me.
Oh, okay. You could be right. Yeah, you could be right. I hadn't thought about that. What is a function that you would use? I'm going to write down here. So this is an aside. I'll just say aside. What would you use if you had something like that? What would that suggest? What would you suggest for the one that I drew there?
Exponential?
Yeah. So, but what would you exponentiate? You'd exponentiate the y, right? So here you have y, here you have x. So you would you'd exponentiate y if you had that kind of data, right? What if you had something like that, which we see up there in D? So here, in this first one, you'd exponentiate y, and then do a linear regression, right? That's the approach you use there. But what if you had this kind of pattern? In this case, I would exponentiate x. Or I should say, actually, let me just back up just a sec. What you do is you take, in this first case, you take log of y, right? And then do a linear regression. In this case, the same thing, but you do it on x. So you do, so you take log of x and then do linear regression. But you can then, in your graph or whatever, you can exponentiate back to see the pattern. right? But that's what you do in those two types of cases. So actually in here, I would try that actually. I would try a logging X to get that relationship between prestige and income. And the benefit of that, you know, if we try a quadratic, what's the downside? Well, that curve is going to start coming back down, right? But if we do this approach, it would be, we'd have like an asymptote, and that line would keep moving towards it, but it wouldn't come back down. I guess you could try like a cubic pattern. Any other thoughts for modeling that? Something that we talked about? I'll get you guys involved here so I can take a break from talking.
Could we put a
Go ahead, Laura.
Could we put a knot in at that change point?
Yeah, that's what I was thinking. Like if you look at this, almost seems like you're joining two lines, right? So you could maybe put a knot like right around here and join two lines together, right? I guess the question is there something that would really suggest that you have a hard change point, you know, and maybe, you know, maybe you do, maybe you don't. That would be the one maybe downside, is that you lose the smooth function. But by looking at that I had thought about that as well. So maybe one knot and do a piecewise regression. Jonathan mentioned the gamma, so we could try that. So do gamma question mark. Maybe that's a thought as well. So that's all I have. If anybody wants to hang around and talk about projects and stuff, we could do that. But I'll stop the recording here.